Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Water on Earth. This is a student reader in Unit 3. Water's distribution. In August 2015, scientists in England received a surprise in the mail. It was a postcard that has spent the last 109 years in a bottle, traveling the world's oceans. This postcard is the oldest message in a bottle that has ever been found. The postcard had a note written on it. It promised a shilling to anyone who returned it to the Marine Biological Association of the UK. A shilling is a former British coin. The postcard in the bottle was sent out because scientists wanted to understand where ocean water moved around the planet. For centuries, people have dropped messages in bottles to study the movements of ocean currents. Ocean currents are the paths of flowing ocean water that push warm and cold water to different parts of the planet. Ocean currents are constantly moving water around the planet. The movement of ocean currents is complex. It is affected by Earth's rotation on its axis, how much salt the water holds, the temperature of the water, land formations on the ocean floor, and wind. Because of this, ocean currents involve interactions of different Earth systems: the hydrosphere, all of the water on Earth; the geosphere, Earth's landforms, including rocks and soil; and the atmosphere, the mixture of gases, dust, water vapor, and other molecules above Earth's crust. The postcard in the bottle was found on a beach in Germany. It was one of 1,000 bottles released in the North Sea between 1904 and 1906. Slightly more than half of the bottles were returned to the scientists. The rest were believed to be lost at sea. It has been so long since the bottles were put into the ocean that the United Kingdom no longer makes shillings. The Marine Biological Association had to find a shilling on eBay after they received the postcard in 2015. Scientists continue to study ocean currents today. However, they now use different technologies. For example, scientists sometimes attach tiny electronic tags on fish that track where they have been. Oceans on Earth. Earth is a water planet. Oceans cover around 71% of Earth's surface. There are 5 oceans on Earth: the Arctic Ocean, the Atlantic Ocean, the Indian Ocean, the Pacific Ocean, and the Southern Ocean. However, water flows between these oceans because they are not actually separated. Instead, they form one massive body of water. This is why scientists have used messages in bottles. The currents carry the bottles on their journey around the planet. Oceans get very deep. The average depth of the ocean is 3,688 meters, or 12,100 feet. In fact, the planet's longest mountain range runs through the middle of the ocean. It is called the Mid-Oceanic Ridge, and it is found at a divergent tectonic plate boundary. This mountain range covers 65,000 kilometers, or 40,389 miles. The average depth to the top of the ridge is 2,500 meters, or 8,202 feet. Where is water found on Earth? Oceans make up almost 97% of all water on Earth. They are filled with salt water. Scientists estimate that if the salt in the ocean could be removed and spread evenly over the ground, it would form a layer more than 166 meters, or 500 feet thick. This is the same height as a 40-story office building. The remaining 3% of water on Earth is fresh water. Most of the fresh water is stored in frozen glaciers or ice caps, or underground as groundwater. A small proportion of fresh water is found in rivers, lakes, wetlands, and the atmosphere. Proportion refers to the relationship between things as to size, quantity, or number. Fresh water is important for people. We cannot drink salt water, so most of the water we drink comes from groundwater. Humans and other animals can also get fresh water from lakes and rivers. How water moves. Water doesn't remain in the same place forever. Instead, as the sun heats Earth, energy causes water to move around the planet. As water moves, it causes heat to transfer from the sun through the atmosphere, connecting the hydrosphere and the atmosphere. To understand how this happens, remember that Earth's temperature range allows for water to exist in all three states: solid, liquid, and gas. Water molecules make up the ice found in glaciers and the liquid found in oceans, rivers, and lakes. Water molecules also make up the water vapor gas that mixes with air. Whatever state they're in, all water molecules are made up of one oxygen atom and two hydrogen atoms. The water cycle. With enough energy from the sun, liquid water on Earth's surface evaporates into the atmosphere. Evaporation is the process of liquid water changing into water vapor, its gas state. As the water vapor moves higher in the atmosphere, it loses heat. Eventually, it will condense. When it condenses, it changes from a gas back into liquid water. Precipitation is water falling back to Earth's surface in the form of rain, snow, sleet, or hail. Some of the water that doesn't immediately evaporate back into the atmosphere will collect into lakes, pools, and other water sources. Some water will seep underground. Water that doesn't seep into the ground or get absorbed by plants and animals flows downhill because of gravity. Any area of land where all of the water that falls in it drains into a common outlet is called a watershed. Plants absorb some water through their roots and release it through their leaves as water vapor back to the atmosphere. The process by which water moves through plants from roots to their leaves and into the atmosphere is called transpiration. The circulation of water from a collection to the atmosphere and back to the surface is called the water cycle. How oceans get salty. The movement of water on the planet connects all of Earth's systems. For example, water vapor is held in the atmosphere. Another gas found in the atmosphere is carbon dioxide. When water falls to Earth's surface, it is slightly acidic because it carries some of this carbon dioxide. This slightly acidic water causes chemical weathering of the rocks on Earth's surface. This interaction is between the geosphere and the hydrosphere. The chemical weathering breaks down the rocks, transforming the matter into new substances with different properties, including salt and other minerals. All water that collects on Earth's surface will eventually flow downhill because of the pull of Earth's gravity. As water flows downhill, it erodes the particles of salt and other weathered matter. All water eventually ends up in the ocean, where it deposits the salt and other matter. Over millions of years, this salt has collected in the oceans, resulting in salt water. Weather and climate. The Gulf Stream. In the 1700s, there were no telephones. People who wanted to communicate with people overseas had to send letters on ocean vessels. Because of this, Benjamin Franklin was very interested in ocean currents. Franklin was curious about one current that flowed eastward from the Gulf of Mexico around the southern tip of Florida and along the east coast up to Iceland and Norway. This is the Gulf Stream. Franklin was the first person to chart its movement. On several trips across the ocean, Franklin took the temperature of the water as he crossed over it. He found that the Gulf Stream is like a warm river that moves through the colder waters of the Atlantic Ocean. He realized the Gulf Stream could speed up the travel time of boats sailing between America and England. They would have to stay in the current when they traveled east and avoid it when they traveled west. Earth's climates. In addition to helping boats sail the oceans more quickly, ocean currents have another important function. They transfer heat around the planet. This is important because Earth's surface is not heated evenly. Remember that Earth is a sphere. Around its middle, the sun's rays shine directly onto the planet. This middle point is called the equator. The equator is the imaginary line that runs around the widest part of Earth. It is halfway between the North Pole and the South Pole. This region around the equator is the tropical climate zone. The sun's rays are the most concentrated here. This causes the temperatures to be the highest. The sun's rays spread over a large area when you move north or south of the equator. This causes Earth's surface north and south of the equator to receive less direct heat from the sun. As a result, these regions have lower temperatures. Oceans transport heat. Earth's land, oceans, and atmosphere all absorb heat from the sun. But the oceans absorb the most. This means that the tropical waters around the equator absorb the most heat. As the ocean absorbs sunlight, its surface warms. With enough heat, the water moves into the atmosphere as water vapor. Evaporation increases the temperature and humidity of the surrounding air. This then causes rain and storms that are carried by winds around the planet. The water cycle is very influenced by these interactions between the atmosphere and the ocean. In fact, the ocean is the primary source of the water cycle. 78% of all rain falls onto the ocean, and 86% of all water evaporation comes from the ocean. Ocean currents also carry warm water and precipitation from the equator toward the north and south poles. They carry cold water from the poles back to the tropical region. Oceans influence climate. As they absorb heat and transfer it and water around the planet, oceans influence Earth's weather and climate. Weather refers to the conditions of the atmosphere: temperature, humidity, wind speed, air pressure, and precipitation in a particular place at a particular time. Climate is the average weather over a span of 30 years. Weather changes hour to hour. Climate changes over very long periods of time. How close a region is to the equator affects its climate. So does its nearness to the ocean and its elevation. Because tropical regions receive the most direct sunlight, they also experience the most rainfall. This rainfall is mostly over the oceans. They also tend to have a wetter and warmer climate. Regions that are at higher elevations are farther away from the ocean, and farther from the equator tend to be cooler and drier. How hurricanes form. As oceans interact with the atmosphere, they cause weather events. For example, a hurricane is a storm system with strong thunderstorms and sustained winds of 119 to more than 252 kilometers per hour. Hurricanes form when ocean water is hot enough to quickly evaporate into water vapor and condense into large clouds. Because of this, hurricanes always begin over warm ocean water near the equator. Hurricanes are then moved by global winds called trade winds that push them from east to west. Hurricanes begin when evaporation makes the air above the ocean humid and warm. Humidity is a measure of the amount of water vapor in the air, compared to how much water vapor the air can hold. A 0% relative humidity means that there is no water vapor in the air. When relative humidity is 100%, the atmosphere is full of water vapor. Some is released as precipitation. As evaporation makes the air warmer, that warmer air rises in the atmosphere. At the same time, cold air sinks, creating wind. Winds coming together force air upwards. As humid air rises, it creates clouds. Winds from outside the hurricane push the storm from east to west. Hurricanes can grow more than 800 kilometers wide, with winds more than 252 kilometers per hour. They grow stronger when there is warm, moist air. When a hurricane reaches land or cooler water, it weakens because it has no more water or heat to fuel its growth. Hurricanes and people. Hurricanes can impact living things. The heavy rains can cause flooding. The strong winds can uproot trees and sometimes even buildings. Because of this, scientists have developed tools to predict the strength of hurricanes and the path they are most likely to travel. For example, scientists know that hurricane activity is greatest in late summer. This is when the difference between air temperatures and sea surface temperatures is the greatest. In the Atlantic Ocean, hurricane season generally runs from June 1st to November 30th. However, late August and all of September are the most active hurricane months. Scientists use the Saffir-Simpson hurricane wind scale to categorize hurricanes. This scale describes how much damage a hurricane might cause as it develops. The scale classifies hurricane by wind speed. It goes from a dangerous Category 1 to a destructive Category 5. Category 5 hurricanes only form about once a year. So here's the Saffir-Simpson hurricane wind scale. So here's tropical depression stage, a storm system with heavy rain and winds, wind speed 62 kilometers per hour or less. Tropical storm, a storm system with strong thunderstorms and sustained winds, wind speed 63 to 118 kilometers per hour. Category 1, very fast winds that produce minimal damage from flying debris. Wind speed 119 to 153 kilometers per hour. Category 2, extremely fast winds that cause moderate damage from flying debris. Wind speed 154 to 177 kilometers per hour. Category 3, winds that cause major damage, including window blowout. Wind speed 178 to 208 kilometers per hour. Category 4, winds that cause extensive damage, roofs and walls collapse. Wind speed 209 to 251 kilometers per hour. Category 5, catastrophic winds and home destruction. Wind speed 252 kilometers per hour or greater. Problem of water pollution, the Everglades. During half of the year, part of southern Florida is covered by a slow-moving river. This river is filled with sawgrass marsh, so it is often called the River of Grass. This river is part of the Everglades, a region of tropical wetlands covering 1.5 million acres of land. Wetlands have three defining features which connect all of Earth's systems. 1, they have the ability to hold water, hydrosphere. 2, they have moist or wet soil, hydrosphere and geosphere. And 3, they are home to water plants, hydrosphere, geosphere, and biosphere. The Everglades are an important part of the water cycle. Because of their location on the coast of the Atlantic Ocean, the Everglades experience strong thunderstorms and sometimes hurricanes. These storms provide abundant water that cycles through the region. Part of the water cycle. There are 2 seasons in the Everglades, a dry season and a wet season. The dry season lasts from December to April. The wet season lasts from May to November. During the wet season, the Everglades become a river that is shallow but miles wide. It moves so slowly that it's almost impossible to see. Life in the Everglades depends on the natural cycling of water. The wetlands play another important role in the water cycle. They improve water quality because they act as natural filters. Filtration is the process of separating solid matter from a fluid by having the fluid pass through the pores of another substance, called a filter. The Everglades act like a strainer. As water moves from Earth's surface through the Everglades, it is filtered, becoming purer. For example, some plants in the Everglades take pollutants into their roots and change them into less harmful substances. By the time water has moved through the Everglades, many pollutants have been removed. Environmental threats. But the Everglades face many different environmental threats. An environmental threat is anything that can cause harm to the environment. For example, scientists realized that human activity was causing so many pollutants to enter into the water that the Everglades couldn't filter them all out. This goes back to the water cycle. As rain falls, some of the water is absorbed into the ground. Whatever doesn't absorb into the ground or get used by plants and animals can become stormwater runoff. Runoff happens when water, along with the substances carried in it, flows from the surface of an area of land, a building, or a structure. This runoff carries with it sediment from the ground, as well as bacteria, fertilizers, pesticides, oil, and other contaminants. In recent years, scientists have focused on conserving the Everglades. Conservation is the weighing of human needs against the needs of the environment to create a sustainable way for humans to live off of natural resources. Conservation comes in many forms. In the Everglades, it has included setting aside some of the land as a national park and cleaning up polluted rivers. Engineers solve problems. Teams of conservation scientists and engineers are working on the problem of water pollution in the Everglades. Engineering is different from science, although science and engineering are connected. Scientists use experiments to gain knowledge. Engineers use that scientific knowledge and mathematics to solve problems by creating new technologies. A technology is anything made by engineers to solve a problem. Technologies fulfill human needs or wants. Similar to how scientists follow a scientific process to answer a question, engineers also follow a process. Engineers often follow a process with 8 steps that guide them as they create technologies. The engineering process begins with a problem. In the Everglades, one problem was water pollution that harmed the surrounding environment. When engineers are defining a problem, they include the criteria. The criteria are the needs the solution must meet. They also include the constraints. Constraints are ways the solution is limited. Materials and cost are 2 common engineering constraints. Once they have identified the problem, engineers need to research it and find out what is known about the problem. For example, engineers researched where the main source of pollution in the Everglades were coming from. They realized that much of the pollution came from fertilizers used by farmers and polluted stormwater runoff. They also researched the filtration benefits of the Everglades. For example, engineers need to know that porous materials allow water to flow through them easily. They also need to know that some materials filter water better than other materials. After engineers have researched their problem, they survey the available materials. This survey includes a sketch of the material, as well as how much of the material they have available and the properties of that material. For example, engineers need to think about the porosity of the materials they are planning to use. The smaller the pore size is, the purer the water will be that flows through it, because everything that cannot fit through the pores will be filtered out. Engineers then come up with possible solutions for how the problem can be solved with the available materials. For example, many communities use filters made of sand, gravel, soil, or other porous material around storm drains to treat storm water runoff. As runoff water enters the storm drain, the filter can strain out pollutants before they enter the storm drain. This solution helps to prevent pollution from becoming part of the water cycle. Engineers then diagram and build a prototype. A prototype is a scaled-down first draft of a technology. Once built, engineers test the prototype. They use the tests to gather data, which are measurements and observations that capture how well the prototype solves the problem during testing. Engineers who want to know how well their storm drain prototype filter works test it to see how many pollutants it filters out before the water reaches the Everglades. So here's an example of a water filtration prototype. Finally, Engineers use their data to decide whether to refine or replicate their prototype. The data tell engineers how well their prototype technology solved the problem. Following an engineering process. 1. Problem. Identify the problem, including the criteria and constraints of the problem, and summarize in 2 or 3 sentences. Research. Use what you know to help solve the problem. Record a minimum of 3 facts relevant to the problem. Survey available materials. List the available materials that can be used to solve the problem and include for each material a sketch, quantity, description, and properties. Possible solutions. List 3 ways the problem can be solved with the available material. Diagram and build prototype. Draw a hand-sized scientific diagram of the prototype solution you will then build from your materials. A scaled-down version of a technology is called a prototype. Title the diagram and include labels for each material or part of your prototype. Test. Test your prototype to see how well it solves the problem. Data. Collect data, measurements, and observations as evidence for how well the prototype solves the problem. Refine or replicate. Use your data to evaluate the success of the prototype and recommend if it should be refined or replicated. You may redesign your prototype to better solve the problem. Every conclusion must contain a minimum of 3 elements. 1. Restate the problem and describe the prototype technology. 2. Make a claim about whether the technology should be refined or replicated. And 3. Use key points of data gathered from testing to support the recommendation to refine or replicate. Innovations versus inventions. When an engineer develops a completely new technology, it is an invention. So the first telephone was an invention. The first automobile was an invention. When an engineer improves an existing technology, it is an innovation. There have been many innovations in the telephone and the automobile. Some are shown here. Wow, I learned a lot reading Water on Earth, and I hope that you did too. I'll see you tomorrow with another one. Have a good day. Bye.